folks, welcome back to Physics with Captain Rod. I'm making this video to kind of demonstrate how to write momentum equations for a two-dimensional, perfectly inelastic impact. So in this example, imagine we have two cars with equal mass. And the first car here, I'm going to call it car A, is moving, let's say, east at 20 meters per second. Car B is moving south at an unknown velocity. They hit at an intersection and get kind of tangled together. And the system can be shown here moving at a velocity v2, 50 degrees. That would be south of east. So, the important thing here is how to analyze this problem. And what we want to be able to write for this is we want to be able to write kind of before and after equations. What types of things are the same before and after? And the one thing that's not the same is kinetic energy. Right? There's going to be substantial kinetic energy loss when these two cars collide, as evidenced by all the damage. The key concept with momentum is that when these cars collide, the force exerted between car A and car B is kind of like down and left on car A, kind of up and right in the picture on car B. The important thing is, as long as we define our system as both cars together, the net force on the system is zero, and therefore we can say momentum is conserved. So that allows us to write two equations, because remember, momentum is a vector concept. That means we can apply it by direction. So I'm going to go ahead and write one equation. It's going to be conservation of momentum, x direction, and I'm going to call it to the right positive. So looking at my picture, here's the car that's got a momentum component in the x direction. So that's going to be mass of car A times what I'll call for now VA1. That's velocity car A, picture 1. This is my picture 1 before the impact. Picture 2 is after impact. The VA1 is the 20 meters per second. That's going to equal, looking on the right, the x component of the momentum of the system. Now the momentum of the system is mass times that velocity vector right there. And because these two cars are acting as one mass, the mass of the system is the sum of the two. I'm going to go ahead and put mass A plus mass B, right, times V2. That is now the magnitude of the momentum vector. And then I'm going to put times the cosine of 50 degrees, so that I'm only picking off the x component. So basically what I'm doing is taking the momentum of car A, which is here, equating it to the x component of the momentum of car B, which is going to be the mass times V2 times cosine 50. And here's the following equation here. Taking note that these cars now, according to my assumption here, have equal mass. That means this will add to 2m, and the masses will divide out. So this will simplify to VA1 is going to equal twice V2 cosine 50. And I'm going to go ahead and solve that for V2. And I get about 15.6 degrees. So I'm going to go ahead and write that up here. I'm sorry, not degrees, 15.6 meters per second. All right. So I now know V2. Another unknown in this problem is VB1, velocity of car B, picture 1. We can get that by writing another momentum conservation, con of mom. I'm going to go ahead and put y direction and down positive. So looking at our picture, picture 1, this is the car that has a momentum y direction. So that momentum is going to be mass B times VB1. It's positive only because I've defined it down as positive. Had I defined up as positive, that would be we'd put a minus sign in front of that. Right? That has to equal the y component of our momentum in this picture. Looking at that picture, we've got a velocity of v2. The momentum vector is going to be the mass of the system, which again is the sum of the two. They're stuck together. Times v2 is the magnitude of the momentum vector times sine 50. Okay? And again, these masses are equal, so we can just basically call it m, and we can kind of write that term as 2m. And the mass will divide out with this one, so we're going to get VB1 is equal to twice V2 sine 50 will be the next line. We go ahead and solve that for VB1, and I get about 24 meters per second for VB1. Now, just to keep this video short, I'm not going to do this, but we could calculate the total kinetic energy in picture 2. We could calculate the total kinetic energy in picture 1 by adding the two kinetic energy terms together. What we'll find is that the initial kinetic energy is quite a bit greater than the final kinetic energy. There's going to be a substantial loss, as there usually is in impacts. It's only kind of special cases where energy is conserved. So anyway, I just wanted to provide an example of how to write two-dimensional momentum equations. And there they are. Hope everybody has a great day.